Good morning friends, welcome you all to final part of hydraulic calculation video. I request you to watch the previous chapter's hydraulic calculation video before watching this for clear understanding. Video links I have given in the description. Till node number 5 to 6 I explained in the previous video. Now let's start from node point 6 to 7. Then coming to 6 to 7, if you see here 6 to 7, I didn't add the flow. Because the same flow of 119.36 from the previous node I followed, because the 6 to 7 it is not in the hydraulic area, okay, but you have to find out the pressure drop. So that is the reason what I did. I consider the 6 to 7 same flow, and here the pipe size is 2 inch, like you see here it is 50 mm, and the total length 24.6 feet. So how I got this total length, like you can see in this image. Okay, here the total from 6 to 7 you need to consider, plus this 7 to this point, there is a small gap is there na? So we have to consider this total length from 6 to 7. Okay, in our case now how much here, if you see here 6 to 7, this 3 meter plus 3 meter plus 1.5, total it will be 7.5 meter. So 7.5 meter, 7.5 into 3.28, so it is 24.6 feet. So this 24.6 feet I added here, and the pressure drop same from the table, friction loss table, you know how to find out, and you have to multiply the total with this the total length, and you have to add with the earlier pressure drop. Same for the fittings, you have to consider the same step, you have to repeat. Okay, now here one more important point is you need to consider the riser nipple T, because here as per NFPA there are two different cases are there. The first thing, in this case if you see here, this is the riser nipple top T and this is the riser nipple bottom T. Actually this is the cross main and the riser nipple is here, and this is the left side line, this is our line, and right side line. So there will be a T here and also one more T in the cross main. Okay, so which node we need to consider this T and which node we need to consider this T. Okay, so NFE has a good reason for this one. If you see this point, I'll show you. So here as per NFA what they mentioned, the T at the top of the riser nipple shall be included in the branch line, T at the base of the riser nipple in the riser nipple itself. So here if you go to our image, okay, here the T at the top of the riser nipple, that means this T that should be part of the branch line. The T at the bottom of the riser nipple, that will be part of the riser nipple. Okay, so we have to follow this one. So here for node number 6 to 7, I consider the top of the riser nipple T. So as per the rule, top of the riser nipple T I need to consider in the branch line. So I consider that T also in the for the friction loss. Then 7 to 8. The 7 to 8 is that riser nipple height. So here in our case it is 200 mm I consider. Okay, so see, there is no fixed rule that we need to consider 100 mm or 150 mm or 200 mm. It is based on the site condition. So the maximum height should not exceed 600 mm. If it is more than 600 mm, then you have to provide the support for this riser nipple also. That's practically we are not doing. So that's why we are keeping less than 600 mm. So how the condition happen is, for example, you have the slab here, and here we have the riser main. And from the riser main I am taking the branch line which is going right and left, so it has to go like this, and here we have the sprinkler. Okay, and here what happened, the distance between the slab bottom and the sprinkler deflected top, so this distance is normally 25 mm to 300 mm, minimum 25 mm, maximum 300 mm. For example, consider you have the HVAC duct is passing here. So we have to adjust the height. We have to adjust the height going down. From here it will go like this. Okay, so this right, and again in this point one a cable tray is passing. So you have to adjust this height, the cross main to the branch, this pipe. Also you have to adjust this pipe. Okay, so the split pipe and the riser nipple pipe we have to adjust. Okay, there is no fixed rule, but if it is exceeding more than 600 mm, then you have to provide the additional support. Okay, so that's the point. So in our case I consider 200 mm for the riser nipple, so it will be like 0.2 into 3.28 the total length. So you can get the answer here. For example, here 0.2 is a 0.2 means 200 mm into 3.28 is the meter to feet conversion. Okay, so again the same pressure drop I repeated for the pipes, then for the T. And that coming to 7 to 8, if you see here riser nipple bottom T I considered in the riser nipple itself. Okay, as per the NFPA 13. Then going to 8 to 9. So 8 to 9 there is no sprinkler, so it will be NSP. no sprinkler, 8 to 9. The flow you see, still I followed the same flow because there is not in the hydraulic zone. Okay, so pipe size is different. The length is 11.8 because this is here 3.6 meter. So 3.6 meter I converted to feet. 3.6 into 3.28, it is 11.808. Okay, so that length I followed here, and the same step you have to consider for the friction loss. And coming to the fittings, the riser nipple bottom T, that means if you go to that point here, okay, 8 to 9, there will be a riser nipple here also, and also going down, going further, there will be a riser nipple at each junction. Okay, so this riser nipple bottom T also we have to consider in the calculation. So 8 to 9 is done. 9 to 19, there is an important point we need to consider here. For example, if you see here 9 to 19, so here okay, I'll tell you first this reason. 9 to 19, I have to add the sprinkler in the hydraulic zone, that flow to this node 9 to 19. Okay, so here for example 10, 11, 12, 13, 14, 15, all this node I don't want to add here, because the reason here is when you go to 9 to 19, you can directly add the flow of all this sprinkler to the 9th node, because as I told you earlier, this area we are not going to consider the pressure drop for the pump. This area also we are not going to consider the pressure drop for the pump, because the last residual point mean from the pump we need to consider the last point till here, mean this is the highest root of pressure drop. So if the pump can throw the water till here, it can also throw the water to here and here. So that's the reason these two area, the pressure drop I am not going to consider. So you don't need to add the node point also here. Okay, but the only thing you have to do, you have to add all this hydraulic area, this 5 sprinkler, 1, 2, 3, 4 and 5, not this sprinkler. So this 5 sprinkler flow you need to add at this node. That's enough. Coming to 19, you can add this 3 sprinkler flow at this node. That's enough. So you don't need to add this, you don't need to provide the node point like 10, 11, 12 is not required, because we are not considering the pressure drop. And also here also no need to provide the node point. Okay, I just added here for your understanding. So coming to point number node, now I am going to add the sprinkler flow. Same like see, if you see here, till this point it is 119.36. Okay, that means the 5 sprinkler flow, node number 1 to 5, it is 119.36. So node number, at node number 9, the same 5 sprinkler flow I am going to add. That means I am going to multiply with 2. That's all. So if you see here 119.36, I added 2 times. So that is the flow at node number 19, node number 9. 9 to 19, I added this full 5 sprinkler, I mean the hydraulic sprinkler flow. Okay, so coming to 19 to 20, what I will do, I will add this 3 sprinkler flow. That's all. So one sprinkler flow is 18 GPM. So 3 sprinkler flow I will add here. So here 9 to 19, I added the same previous node into 2, then 2.5 inch, that is the length, and the total the length is 3.6 meter. It is 11.808 feet, and from the table you can find out the pressure drop. Okay, the same step. Coming to 19 to 20, this is the important thing. Again, I told you we have to add this 3 sprinkler flow, 17 to 18, this 3 sprinkler flow. So from the earlier calculation, we know that for each sprinkler we got 18 GPM. Okay, so that 18 GPM we need to add here, like you see here. The sprinkler for one sprinkler flow is 18 GPM. So we need there 3 sprinkler. Okay, so that we need to consider the 3 sprinkler flow from 17 to 18. You don't need to provide the node point also, directly you can add. So at this point what I did, I added the 3 sprinkler flow 3 into 18. Okay, with the earlier flow. So it is 292.72 GPM. And here the total means the pipe dia is changed now, because here if you see is 19 to 20. I'll open the another drawing. Okay, here. So here is 19 to 20, not this point, 19 to 20 till here it is 3 inch. Okay, so we have to add this 3 inch and the equivalent flow, then you can find out the answer. For example, here 19 to 20, 292.72, after adding the 3 sprinkler flow is 3 inch, and total length is, if you see here, the pipe size is same. Here the reason is the pipe size is same, and also it is not in the hydraulic zone. So that is the reason I just added two length together. Okay, otherwise I would have added the node here 20. Okay, the pipe size is same, no? That's why I just skip the point. So here now for this 292.72, we need to find out the pressure drop. So I will show you the table again. 292.72 mean we can round off to 293 GPM. Okay, so here if you see here is for the 3 inch pipe, and so for the 3 inch pipe, so 292 means you can make 293. Okay, the next step you can follow, that means the nearby one. So here we have 293 GPM, like you see here. at this point 293 GPM, and the flow the pressure drop is 0.1003. Okay, so similarly for the 3-inch pipe, if you want to find out any fittings like elbow, T, this equivalent length you can consider from here. So again here I applied the same in the formula, and you have to multiply with the total length, and for the pressure drop you have to add with the previous stage pressure drop. Okay, same for the T also you have to repeat. Okay, so what I told you, the T in the branch, that means the path of the hydraulic zone. For example, here this T, and here also riser nipple will be there. So all the riser nipple bottom T we have to consider in the calculation. So the next step is, now we did 19 to 20, coming to 20 to 21. Here there is no, it's not in the hydraulic area again, and the pipe sizes are same. So I consider as a single node 20 to 21. Okay, so this length again you have to add, but practically saying 3.5-inch pipe is not available. Okay, so when you go for the hydraulic calculation, as per NFPA 3.5 pipe size is there, but practically it's not possible. No? We have to follow 4-inch. So in the hydraulic calculation also you have to consider 4-inch. Okay, so here if you see here this node point 20 to 21, I added 4-inch only. I didn't consider the 3.5 inch, so that's not practical. Then going to the next point 21 to 22, again it's not in the hydraulic zone. So the flow we have to consider as much as the length we can go to save the node point. Okay, and here the pipe size are same, so I just saved the node from 21 to 22 here. Okay, at 22 to 23 what will happen? There will be a elbow. So here 19 to 20 the same flow, 20 to 21 same flow. Again the flow will be same till the fire pump reaching last point. Okay, because that is not in the hydraulic zone, we are following the same hydraulic flow till the last point. And here 20 to 21, and here the pipe size I added same like other step I followed. Pressure drop of the pipe, pressure drop of the fittings, and 21 to 22 also same, and 22 to 23 here if you see there will be a elbow. 20 to 23. So the elbow point I added here NSP EL. NSP means no sprinkler point. EL means elbow. Same flow. The pipe size is 4-inch. The equivalent fitting length is 10 feet. And the pressure drop also you see for all the this one the same flow, same size, same pressure drop. Okay, it will not change. Then next going to 23 to 24. This is one important thing. 23 to 24 we have the zone control valve. So like you see here zone control valve, we have to consider the butterfly valve pressure drop. We have to consider the water flow indicator, but this pressure gauge attached in the main line we don't need to consider because this is not obstructing the flow. Okay, this is top of the pipe, it is not in the pipe. Okay, that is the reason we don't need to consider. Also this drain piping also, this tie-in point also we don't need to consider as per the NFPA 13. So here the first one is the butterfly valve. So butterfly valve, if you see our hydraulic chart which we are doing so far, so you need to consider the same hydraulic friction loss table. For the 4-inch pipe, gate valve, check valve, alarm valve and dry valve they have given. The butterfly valve is not given, so we need to consider the butterfly valve. So what I did is, in the chart I couldn't find, so I just followed the Elite software butterfly valve calculation. For example, if you see here, it is given like 45-degree elbow, 90-degree elbow, and long turn elbow, T, cross and butterfly valve. So I just took the answer of equivalent feet from the software for the butterfly valve. Okay, so in this fitting you can see one fitting, only one fitting you cannot find out in the software also, that is called as reducer. Okay, so there is no reducer in here, there is no reducer here, so you cannot find out the reducer fitting in the Elite software also. So here for the butterfly valve I consider the equivalent feet of 13 feet from the software, and for the water flow indicator, normally water flow indicator software as well as manual calculation we cannot find the value. This value we need to get from the manufacturer. Okay, so manufacturer we need to get the equivalent feet of pipe for the product, their product. Then second thing, the pipe, for the pipe if you see here at this point 23 to 24. Okay, 23 24, and I go also in the another image. So 23 to 24, this length, the straight pipe for the zone control valve area from here to this point. Okay, so this fitting this pipe length also we have to consider. So here 23 to 24 we discuss about the butterfly valve, water flow indicator and the straight pipe. The next one is now 24 to 25. So 24 to 25, the important thing here is, if you see in the drawing this point 24 to 25, at this point, like you see here 24 to 25 this point, or 24 to 25 this point. So in this image you can see it's like 24 to 25 is like a elbow, but actually saying it's not an elbow, it will be a T. Let me show you that. So here you can see the zone control connection is coming, and here there will be a T. On top of the T there will be a air vent. Normally in the riser will be like this, and there will be different zones, different rooms. There will be different zone control will be installed here in the different floors. So top of the riser there will be a air vent. So we are here at this point. So this fitting is normally the practically saying is a T, but in the isometric it is mentioned like shown like a elbow. So like you see here, it's shown like a elbow, but it should be extended here, and it should be a air vent. So we have to consider this point as a equality. So here 24 to 25, 4-inch pipe, the same flow, 292.72 GPM is not a fittings. I consider means this is the straight one. So I consider this is not the pipe, this is the pipe, and this fitting is 20 feet. This 20 feet I consider from the friction loss table that I will show you again. If you see here is a 4-inch steel pipe, and the T is from here. So this 20 feet equivalent length I consider. And coming to the flow is 292 GPM. So the next one is 300 GPM. This is 290. The next one is 300 GPM. And C120 for the wet pipe system steel pipe. And the friction loss is 0.0279 PSI per feet. So here I added the equivalent length of the T 20 feet. And this is the friction loss for 1 feet. And finally the total friction loss is multiplication of total equivalent length into friction loss. So this is the friction loss we have, and I added with the previous point friction loss. And the next one is 24 to 26. This is very important thing, because the alarm check wall, all these assemblies will come here. So if you go to this image, you can see this one, the 25 to 26. At this point the vertical pipe is 43 meters. So this pipe friction loss we need to consider. After that, the important thing is this alarm check wall assembly will come. So let's see how to get this value. So if you see this friction table, same 4-inch pipe, the alarm check wall value is given for the C120 steel pipe material. So we have to consider this 20 feet equivalent length for the alarm check wall. So here same arrangement, 20 feet equivalent length I consider for the alarm check wall, and the same friction loss, because the flow I didn't change, same like 292.72, the same flow friction loss. And finally we will get the total friction loss that I will add with the previous step friction loss. And the next one is the pipe, for the pipe we need to consider the friction loss, and the total length is 43 meter. From this one you can see it is 43 meter as I mentioned here. So this pipe friction loss also I have to add here. Then 43 into 3.28 I convert to feet, and this arrangement the same friction loss 0.0279 and the total friction loss. Then I added with the previous stage friction loss. So this is done. So 26 to 27, finally now we have one elbow, you can see here. So in this image you can see this 26 to 27 there is a direction change. So there will be a elbow, but practically saying there are two chances. Like if you have the riser like this, as I told you, in the top we have the air vent. Similarly in the bottom mostly we will install the drain riser. So that time it will be like a T. Okay, so the drain riser point will come here. There will be a equal T, and the pipe will go here. This pipe will be here. So this will be a drain riser normally. So if you have that point, you have to consider the same like our air vent, how we consider the equality. Here also you need to consider the equality, and below you will have the riser. So at this point I consider like a 40 I consider like a elbow. And for the 4-inch steel pipe I consider this 90-degree elbow, that is 10 equivalent length feet. So the equivalent length value I added here, and the friction loss is still same, and the total friction loss that I added with the previous friction loss. So finally the last point is 27 to 28. You can see here 27 to 28, which is going to the pump here. So this length is 5.448 meter. So I added here at the Excel 5.4849 meter multiplied with 3.28 to convert to feet, and same friction loss, and I multiplied with it to get the total friction loss, and finally this is the answer. So here you have to mainly see 2 points. The first point is like in this in the last image you can see here I consider like a straight pipe. This one is I consider like a straight pipe, because in each project it will not be like a straight pipe. So there will be different elevation. For example, the pipe is coming like this. For example, you can see the pipe diagram, the tank diagram. So there will be tanks. For example, here we have the 2 tanks, and the suction header will be here, and suction pipe will go to different pump, jacky pump, same like diesel pump and electrical pump. From the suction header again the pump will come. So this will be again discharge header. So this will be like there will be angle elevation will be there. It will not be like a straight pipe. So you can, like you see here, there will be different elevation will be there. So if there are elevation changes are there, then you have to consider that elevation changes at this point. With the pipes, the elevation changes also you have to consider. Okay, so in this case I consider like a straight pipe. So straight pipe, finally the total friction loss is, we got is 68.923 psi, and the total static head, because static head is important for the pump to throw the water. So in our case it is 43 meter from this area, 43 meter. So I added the same value, 43 meter. So for 1 feet we have to consider 0.433 psi friction loss for 1 feet. So we have 43 meters. So I multiplied with the first we need to get the feet. So 43 into 3.28, we got the answer in feet. Now this answer I multiplied with 0.433 to get the static head loss. So finally the total friction loss, total pressure loss for this pipe is static loss plus the friction loss. So total 129.99 psi is the rated pump pressure rating. So in our case, we need the total flow for the pump is 292.72, but exactly 292.72 we cannot get. We have to go with the next UL rated or approved fire pump flow. So like you see in this table, after 250 GPM we have 300 GPM. So what we need is 292.72 GPM. So we have to go with the next nearest available value, that is 300 GPM. So in our case, the pump flow, the pump rated capacity is 300 GPM and 192.99 psi. That is the selection for the rated pressure and rated flow for the fire pump. So thank you for watching all the hydraulic calculation video parts. So if you have any doubts in the hydraulic calculation, please add your comment in the comment section. Thank you. Bye bye.